Greetings, everyone. I am Dr. Arlo Clark-Foos, and this is our first lecture in Psych 381, Statistics and Experimental Design. So this is a light one, right? At the beginning of the class, we really just need to introduce a whole lot of terminology so you can understand what we mean when I talk about a variable, when I talk about an independent or a dependent variable, and samples and populations and a whole bunch of stuff like that. That being said, because it's lighthearted, I want to also embed a couple of little videos within this to help expand upon my own explanation so that we get a couple of different tellings. I find that when you hear something in 2 or 3 different ways, you're much more likely to understand it. So feel free, if you understand it right away, to skip through that little section if I add in a video. I'm going to add a summary at the end of the second video as well. If you already got it covered, don't feel like you have to watch that extra little bit. This is here to make sure that it solidifies these concepts for you. Okay? So first, let's hear a little bit about the story of Dr. John Snow and the cholera outbreak in London in 1854.
In 19th century London, nothing brought more fear or panic than the yellow flag signaling a cholera epidemic. And the outbreak that hit in 1854 was one of the worst.
Good morning.
John Snow, a London physician, knows he can't help the dying. But he is determined to help the living by figuring out how victims catch cholera in the first place. Today, we know that cholera is caused by a germ, a bacteria in this case, that is spread in human waste. But back then, the prevailing theory held that cholera was carried in a cloud of bad air called a miasma.
Miasma. It can't be miasma. If it's carried in the air, it should attack the lungs. But we know it attacks the gut. It must be something else.
I know what you're going to say. It's in the water. You've been saying the same thing for years.
If it's in the air, we should all have cholera by now.
You could say exactly the same thing for your water.
Maybe. But I just feel I'm right.
Then prove it, John. Prove it.
Snow sets out to do just that with the only tools he has: logic and statistics.
My name is John Snow. I need to know how long your husband was ill.
He visits the homes of victims in a neighborhood called Soho
Did he eat any old fish or meat?
and tries to find anything that sets them apart from the healthy. He then begins to plot his data on a map.
And where'd you get your water from?
The Broad Street pump.
And where does your family get its water?
What Snow was doing, what Snow really originated,
Thank you.
is the basic premises of an epidemiologist. He was looking at the contours and shape of an epidemic.
His careful detective work reveals a compelling pattern. Virtually all Soho cholera victims got their water from a single well on Broad Street. Municipal authorities surprised the Soho neighborhood by removing the handle from the Broad Street pump.
Get the handle off, man.
It's a victory for the persistent John Snow and the power of statistics.
And once the pump was disabled, the cases fell like a skyrocket that was done. It was just over.
I'll take that.
Later, city officials discovered that water from the Broad Street well was contaminated with cholera germs from a leaking cesspool. What John Snow accomplished is now called surveillance and response, and it remains our best defense for combating any disease outbreak.
Tracking the outbreak of disease, tracing it to its source, understanding the causal connections, these are still the basic tenets of public health.
Okay, so I think for now, the most important thing about that story is really how Snow, Dr. Snow, went out there and tried to figure out how he might be able to track the disease. He needed to collect some data, and so he went home by home and asked whether anybody there was sick or had died. And then he went to another house, and you can see this map is actually a recreation of his original map. And each of those little dots in between the various streets are an indication of a home that had cholera, a patient or a person, a family member who had cholera and had died or was still sick. And so what he was trying to do was look for patterns. He collected some numbers, and now he's looking at the numbers and trying to figure out whether or not they're patterns that can tell him anything. And in this case, it turns out you can see a lot of those dots central around that red X in the middle. That's where a particular pump was there. A lot of people got water from that pump, and it turned out the water they were getting had cholera and was infecting them all, the bacteria that leads to cholera, right? And so tragic story in some ways, but an amazing story in other ways, because it was one of the first cases where somebody had used actual data to chart or predict the progress of a disease. Really led to epidemiology, right? A field that is incredibly prescient, right, today. So I guess we can really break statistics up into two different branches. What Snow was trying to do at first might fall largely into the category of descriptive statistics. And descriptive statistics are perfectly well named because descriptive means to describe things, and that's really the whole point of descriptive statistics, right? It takes a whole bunch of numbers. So imagine I got survey data only on 4 or 5 questions, but I asked 100,000 people. Well, if I asked 100,000 people 5 questions, I have 500,000 data points. If I just looked at those in an Excel spreadsheet, they wouldn't make any sense to me. Tons and tons and tons of numbers. Descriptive statistics organizes, summarizes, helps you to then communicate the patterns. It reduces that huge amount of data down into a couple simple numbers. So you've already done the average before in previous classes. That's an example of one descriptive statistic. We're going to call it the mean now that we're in a statistics class, but it's the same concept, okay? The mean is a way of describing a huge data set that couldn't otherwise be easily interpreted based on the sort of large number of numbers that you'd have to sort of observe. Now, the other thing Snow was trying to do was, based on what he observed, see whether or not he could extrapolate some information from that, whether or not he could assume something based on some hypothesis. So Snow believed it to be related to a waterborne illness, although most of the Londoners at the time thought it was airborne, oftentimes walking around with masks or filling their pockets with flowers so that they would smell good, and thinking that it was the bad air that was contributing to it. He believed it was the water. He just needed to find data to test that hypothesis. That's essentially what inferential statistics aims to do, to infer something about a huge population, humans, and how humans, all human beings, would react to this bacteria in the water and whether or not it would predict or lead to cholera. Right? That's a hypothesis about how a sample that you can observe might be related to that larger population. That by itself is the coolest shit about statistics. That means that you or I can study just a small number of people. As long as we've met some basic assumptions about how we collect our data so that it's ethical and it represents the population, then we can learn a ton about the whole population by studying just that small sample. Right? So that's inferential statistics. That's what we're going to cover in the latter half of the class. The first half is really going to be about descriptive statistics. Descriptive statistics you see all the time, right? I'm not really a social media user for the most part, but I'm sure Facebook and Twitter and Instagram are bombarding you with these numbers periodically. You see them on the news, you see them in magazines and newspapers, right? I just pulled a couple of random ones from the Gallup poll website to give you an example of descriptive statistics. They asked thousands of people these questions. And based on their responses, they're able to then summarize the average number of individuals who believe that gun legislation should be more strict, the average number that believe it should be less strict, the average that believe it should be kept as is. And they did that by calculating these simple descriptive statistics from these large pools of data. So I've already started talking about the sample versus the population, but what do I mean by that? Well, let's say I wanted to know whether or not a particular behavioral therapy would help treat depression. Okay, so I've got a control group that's not going to get the therapy. I got another group that's going to get the therapy. We'll elaborate on these control and experimental groups, but for the meantime, think of it as a group of people who will get the therapy from a therapist, and then another group who will get no treatment whatsoever. At the end, we measure their depression. Now, I'm wanting to know how this therapy works on, let's say, all human beings, or all adolescents, or all adults. Well, that population, all adults, is huge. Because if I really mean all adults is my population, that's who I tend to learn about, well, then that includes every single adult in the entire world. I guess we could make it smaller and say, I want to know how this works on American adults, or immigrants who are adults, or some other smaller population, but those are still huge populations. And so it's unwieldy. It's nearly impossible to try and study the entire population in most cases, unless your population literally consists of something as small as, say, I want to study the population of students currently taking Psych 381 in the winter 2021 semester with Dr. Clark-Foos. That's you guys, right? That's a very small circumscribed population of about 30. We can study that. Most other populations we want to learn about are huge. And so that means that we really do need to study samples in most cases. So one thing that's important, of course, is that our sample is representative. So let's say I wanted to know how Americans feel about soccer, right? What most other countries refer to as football. So I go out to try and ask a bunch of Americans about how they feel about soccer, whether they think there should be more soccer on TV, whether or not we have enough soccer bars, and we have enough interest in soccer in general. Do people wear merchandise for soccer teams? And so the first place I go to ask people questions is a soccer bar in downtown Ann Arbor. And I ask a whole bunch of people questions about soccer, and it turns out they all think soccer should be way bigger in America. We all should be paying more attention. It should be on TV all the time. Is that sample, that group of individuals I talk to, are they representative of the larger population of Americans? Probably not, right? I went strictly to a soccer bar to ask questions about soccer opinions. That's a very clear example of a biased sample. But the point I'm making is that when we study a smaller group and we're trying to make some inference about how the larger population looks based on that sample we're observing, then we need to be sure that our sample is representative. It looks in its basic form like that larger population. Okay, so as we move forward into, especially in descriptive statistics, and we start talking about how to calculate a couple of things, you're going to see some formulas. Really incredibly simple formulas, like the formula for an average, right? Where you add up all the scores and divide by the number of scores. But we're going to use symbols, right? Because they're formulas. And what I want you to sort of pick up on is that there will be times when we are using the Latin characters you are used to, right? The A through Z alphabet. But there will also be other times where we are using Greek characters. Now, this is purposeful. When we are studying a sample of individuals, then what we calculate, these are referred to as statistics, and we use Latin characters. So the mean, for example, the average of a sample, let's say the average height of a sample of data, that would be written with a capital M, right? Capital italicized M, according to APA style. If we were talking about the mean of a population, however, then we use this, what's essentially a Greek character, lowercase mu, the little backwards Y looking guy that's there. Similarly, if we talked about standard deviation of a sample, we use lowercase italicized s, and if it's for a population, we use the Greek character sigma, the lowercase sigma that looks like an O with a little flourish there. So statistics are for samples, parameters are for populations. I think we pretty well covered why we need to use samples. Again, think about the United States. If I want to know how the United States feels about a particular issue, it's extremely difficult to study every single person. The recent census during a pandemic demonstrates just how difficult it is to contact every single individual in a population.
The first step of every statistical analysis you will perform is to determine whether the data you are dealing with is a population or a sample. A population is the collection of all items of interest to our study and is usually denoted with an uppercase N. The numbers we've obtained when using a population are called parameters. A sample is a subset of the population and is denoted with a lowercase n, and the numbers we've obtained when working with a sample are called statistics. Now you know why the field we are studying is called statistics. Let's say we want to make a survey of the job prospects of the students studying in the New York University. What is the population? You can simply walk into New York University and find every student, right? Well, probably that would not be the population of NYU students. The population of interest includes not only the students on campus, but also the ones at home, on exchange, abroad, distance education students, part-time students, even the ones who are enrolled but are still at high school. Though exhaustive, even this list misses someone. Point taken. Populations are hard to define and hard to observe in real life. A sample, however, is much easier to contact. It is less time-consuming and less costly. Time and resources are the main reasons we prefer drawing samples, compared to analyzing an entire population. So, let's draw a sample then. As we first wanted to do, we can just go to the NYU campus. Next, let's enter the canteen, because we know it will be full of people. We can then interview 50 of them. Cool. This is a sample. Good job. But what are the chances of these 50 people that provide us answers that are a true representation of the whole university? Pretty slim, right? The sample is neither random nor representative. A random sample is collected when each member of the sample is chosen from the population strictly by chance. We must ensure each member is equally likely to be chosen. Let's go back to our example. We walked into the university canteen and violated both conditions. People were not chosen by chance. They were a group of NYU students who were there for lunch. Most members did not even get the chance to be chosen, as they were not on campus. Thus, we conclude the sample was not random. What about the representativeness of the sample? A representative sample is a subset of the population that accurately reflects the members of the entire population. Our sample was not random, but was it representative? Well, it represented a group of people, but definitely not all students in the university. To be exact, it represented the people who have lunch at the university canteen. Had our survey been about job prospects of NYU students who eat in the university canteen, we would have done well. By now, you must be wondering how to draw a sample that is both random and representative. Well, the safest way would be to get access to the student database and contact individuals in a random manner. However, such surveys are almost impossible to conduct without assistance from the university. We said populations are hard to define and observe. Then we saw that sampling is difficult. But samples have two big advantages. First, after you have experience, it is not hard to recognize if a sample is representative. And second, statistical tests are designed to work with incomplete data. Thus, making a small mistake while sampling is not always a problem.
So how do we get numbers out of behaviors? We're psychologists. We're not studying things like temperature most of the time, where we can just take a thermometer and we stick it into a liquid or whatever it is and find out what the temperature is. Instead, we're oftentimes studying constructs that might be difficult to put into some quantified numerical form. So maybe you're interested in the degree to which couples experience love when they are apart versus when they are together. Is it true that absence makes the heart grow fonder? Or is it that being together makes the heart grow fonder? Well, that's an interesting question that we can test by looking at couples that either spend a lot of time together or spend a lot of time apart, maybe have distance relationships. How do we define love, though? So I can make my groups, but now I need to measure something. How do I measure love? Especially if I'm talking about a degree of love. Some people experience more or less love. What sorts of behaviors might I look for that I can quantify? I can write down the number of times it happens. Maybe how often a couple looks into each other's eyes. Well, that's going to be more difficult for the group that's apart. So are we talking about looking at this on Zoom meetings too? Or do we need to look at some other measure? Sometimes self-report's the best. Not always, because there are a lot of biases in self-report, but sometimes just saying, how much love do you feel towards this person right now on a 0 to 100 point scale? The point here is that transforming our observations into numbers is a tricky business and comes fraught with a lot of danger, because if we define it improperly, if I decide I'm going to define love or happiness or something like that by the number of times you smile, what if you're the kind of person who walks around smiling all the time who's not necessarily reflecting of that inner emotional state? If you define it poorly at the front end, then whatever you measure is going to be meaningless at the back end. So really thinking about what behaviors map on to what constructs you're trying to study is really important. Now, thankfully, we are not the very first psychologists out there, right? So a lot of work has been done on a lot of constructs. Not to say there isn't a ton more to be done, but you can do that literature review search and look for ways of measuring some of these variables that already exist. What you'll find is that you'll essentially be classifying those observations, that scale of measurement, however you're going to measure it, into either very discrete observations, meaning all the points on the scale have very specific points on that scale. So we talk about biological gender, okay? That tends to be male, female. There aren't variations between those. They're discrete observations. You're one or the other. The number of people on a city bus is going to be a discrete observation, because it'll either be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, to however many is the max on the bus. You will never have 3.5. right? The average number of people on the buses that day in Chicago could end up being a continuous observation, but the individual observation, the count of how many people were on that bus, would be discrete. So discrete observations take on very specific values, no values in between. By contrast, continuous observations, like the amount of time it takes you to complete a math problem, the temperature of the air outside, it can be 40 degrees, 50 degrees, but it can also be 40.2 and 50.697 and all the variations in between there, right? Discrete versus continuous observations. Has somewhat of an impact later on when we talk about how we look at our data. So, scales of measurement. First of all, I'm never going to get really super specific on the difference between interval and ratio. I might ask you for it, but I'll always give you the benefit of the doubt on this one because I find that's the hardest one to discriminate. So let's go through here. What we're talking about is if I'm going to measure something, a variable in my experiment. Maybe it's something like gender, and I'm not using biological gender, but I use a self-assigned gender, whether that be sort of gender neutral, leaning towards male, leaning towards female, or any of these other variations in between. If I have specific points on the scale, right, and so they're discrete observations, you're this, or you're this, or you're this, or you're this, but you're not in between this and this. If each of those points are purely categorical, there's no order to them, it doesn't make sense to put this one first or that one second, you just place them up there, right? There's no reason to put male before female or female before male, right? Who cares? Whichever order it goes. Those are nominal observations. Those are nominal scales of measurement, meaning the scale itself, the points on the scale, are names alone. They're categories. It's like race. You could put it as white, black, Latino, Asian, Native American, and so on and so on and so on and so on. But you're going to have individual points on the scale. It doesn't matter what order they go in. They're all individual names. There's no blending of one to the other in this sense of the scale. I know biologically, of course, there's mixing. Ordinal is the next step up in a scale where what you're measuring, now the points on the scale are still potentially just names, but they have a specific order to them. So for example, rankings, right? NCAA rankings are huge in basketball and football, all these college teams trying to get ranked so that they can hopefully elevate themselves into the college football championship or the basketball championship or whatever they're trying to go for, right? Same thing goes on in all major sports. These rankings certainly do have meaning. That is, number 1 is thought to be better than number 2, most definitely. And number 2 is definitely better than number 3 and better than number 4, number 5, and number 6, and number 7. At least on the whole, we can agree that that's the case. But what we don't agree upon is whether the difference between the number 1 and number 2 teams, so how good is number 1 compared to number 2, and is that difference between them the same size of difference as we would expect between the number 2 and the number 3 team? Not necessarily, right? Being number 3 just means you're not as good as number 2 and you're better than number 4. Doesn't mean that the difference between you and the number 2 team is the same as the difference between the number 2 and the number 1 team, right? In this case, the points on the scale have an order, but the spacing between each of the points is uneven. If that spacing is even, now we're talking about an interval scale of measurement. There's actual numbers as values, which we can sometimes see in ordinal as well. The distance or interval between the values is assumed to be equal. So if I'm looking at, say, reaction time, and I find that you can press a key in 200 milliseconds, and then in another judgment, you press the key in 400 milliseconds. Okay, I know that the difference between 200 and 400, that 200 millisecond gap, is the same as would occur between 400 and 600 milliseconds, right? Those points on the scale are equally spaced. Temperature is this way in at least 2 different measurements of temperature, right? And so we'll see if you can figure that one out based on what I say for ratio. So ratio scales of measurement are the same as interval scales of measurement, except that the 0, if they measure whatever it is and it comes in as 0, then that is a meaningful representation of 0, of an absence of that measurement, as opposed to we just simply didn't get a measure. So Celsius, for example, Fahrenheit, for example, what does 0 in Fahrenheit represent? So if it's 0 degrees Fahrenheit, does that have any meaning? So I guess let's think about what temperature means. Temperature is a measurement of heat. Right? We can talk about it as a measure of motion since the two are highly related, but let's just call it a measure of heat, okay? How much heat is in something. So then when Fahrenheit hits 0, What does that mean? What does the 0 mean? Does it mean there's 0 heat in that thing? Well, no, we know that's not the case. In fact, 32 is the freezing point of water, according to Fahrenheit, but many other things freeze below 32 in Fahrenheit. Several things freeze below 0 in Fahrenheit, so 0 is really an arbitrary number. How about in Celsius? What does 0 mean? Well, in Celsius, 0 is the freezing point of water. So it means something with respect to freezing point of water, but temperature isn't how hot or cold water is, it's how much heat is in something. And so even at 0 Celsius, we can go below that. We can go to -20 and -30 and -40. And so 0, again, doesn't mean the absence of heat. And so with Celsius and Fahrenheit, we could think of these as interval measures because the 0 is not meaningful. Kelvin, however, if you were to measure something, and we have yet to do it completely, measure something at absolute 0, the 0 Kelvin, 0 degrees Kelvin. This does mean, according to physicists, that there is no heat at all, no particle motion, and that everything has stopped, no heat is being released, it is 0. Okay, so like I said before I started this slide, interval and ratio are very, very similar. In fact, ratio is an interval one where the 0 is important. So I'm not going to knock you on anything where I take off points because you said something was interval when it could have been ratio, but I do want you to think about these different scales of measurement. And in fact, let's watch a real quick video that kind of hopefully helps to sort of solidify that concept before we move on. Okay, real quick, this is sort of table to sort of help you keep track of it. Nominal scales of measurement, always going to be discrete, right? Male, female, black, white, Latino, whatever. Right? They are simply nominal categories. Ordinal, now we have an order to them, but they will still be completely discrete because you're either number 1 or you're number 2 in the rankings. You're either a 5-star restaurant or a 4-star restaurant. You're not a 4.5. You're not a 1.5 ranking, right? They're always going to be discrete, never going to be continuous. Interval, however, sometimes they're going to be discrete. Sometimes they're going to be continuous. It really depends on what you're measuring in that case, right? The difference between points on a scale can be discrete and still have equal intervals, right? They can still have, in fact, that ratio amount, though it's extremely rare to have a ratio variable that is discrete. They're almost always continuous. You can have it happen, right? So, for example, the number of kids on the bus example. How many kids are riding on each school bus? Not the average, but on each school bus. Now, the difference between 4 kids and 8 kids is meaningful, right? That interval is the same as the interval that would be there between 8 and 12 kids. So we meet that interval distinction. We also meet the distinction that 0 here means something. There were 0 kids on that bus, right? But it's discrete because you're never going to have 3.5 kids on the bus or 4.5 kids. It's always 1, 2, 3, 4, 5, 6, right? In these whole numbers. Okay, so hopefully that helped make sense of scales of measurement. Now, let's talk about variables. And I think if there's one sticking point that I see a lot of people make errors on, it may be because they don't understand this simple point. So, the word variable. Variable means it changes. It can and has to have the ability to vary, right? I mean, it's the very nature of the word. And so I've always liked this expression, variables always vary. Okay, so the variable of gender. What are the various points on that scale on that variable? Well, again, let's just take the most simplistic classification and say male and female. That means that the most simple definition of the variable of gender, we have 2 points on the scale, 2 levels. That's important because if you don't have at least 2, if you don't have multiple points on a scale, it is not a variable, it is a constant. Right? We've talked about constants in other classes. I'm sure you know what a constant is. Variables change. So one of the 2 most important variables we talk about in statistics, the independent variable and the dependent variable. Okay, independent variables. Those are what you are manipulating or observing differences between groups to determine any effects on a dependent variable. So let's take a hypothetical experiment where I want to see whether or not one gender or the other is better at solving a Rubik's Cube. So I give them all mixed up Rubik's Cubes, and I simply time them until they solve it. Good luck, it's not the easiest thing to do. And I measure the time for the males to do it, I measure the time for the females to do it. The variable that has changed between my groups, I've not actively manipulated in this case, I can't change gender, is gender, okay? It's got 2 levels, male and female. And then I observe, in this case, the effects of that independent variable, that male-female, on the dependent variable. So the dependent variable is what I'm observing or measuring to look for those differences caused by the independent variable. So in that example, it'd be the time taken to solve a Rubik's Cube. I'd look to see how long it takes different genders to solve that same Rubik's Cube. Independent variable, dependent variable being measured. Okay? Independent is manipulated, not always actively, right? I didn't make you male or make you female, but I put you into groups of male or female to solve that Rubik's Cube so that I could study you separately and compare your scores. Okay? This could be how much caffeine intake affects memory, right? Did you have a little bit of caffeine, a medium amount of caffeine, or a large amount of caffeine? You're probably thinking based on my talking speed that I had a large amount of caffeine, but I just talk this way. Right? You can measure political views and exam scores. And right? How does one variable affect another variable? How does the independent variable and the difference between those levels of the independent variable, the male, the female, the low intake, medium intake, high intake, those are the levels of the independent variable. How do the differences there result in differences in this dependent variable? In addition to those 2 main variables, or at least 2 main variables that we're interested in, we can also have what we might call noise or nuisance variables. Right? Noise is pretty much anything that makes it harder to see the real relationship between your independent and dependent variable. So if I'm trying to figure out whether or not gender affects solution times for a Rubik's Cube, noise is something that makes it harder to see that relationship. So maybe a confounding variable. Let's say I went to go find a group of males and females outside of a high school to do this Rubik's Cube experiment, and there happened to be, 15, 20 kids sitting around outside the school. So I walk up to them and ask if they'll participate. They all say yes. It happens to be a pretty close to even split, 8 males, 9 females, or something like that. But it turns out the males that were there were all there because they were part of a Rubik's Cube club. And the females that were there were part of a swim team, right? And so they had very different skill sets, but for one of those groups, they had a leg up. This is a confounding variable because the variable of experience with the Rubik's Cube, right, one we didn't think about, changes with our independent variable. As we move from female to male, our independent variable, we also move from no experience to lots of experience. This means later on, let's say we find that males are way faster to solve that Rubik's Cube. We can no longer conclude that it was because gender affected solution times because another variable changed at the exact same time, right? They systematically varied together. Now, that might not happen. Hopefully that doesn't happen, but we have to look for confounding variables and try and eliminate them before we collect our data in any experiment. It also may be the case that we just have some extraneous variables. Let's say out of the 16 or 17 students that I recruit for this, and I've got my groups of males and females, what if what if several individuals in each group really got poor sleep last night because there was a great high school football game and they had all attended and they all stayed out late watching the game and then coming home. And so I've got a bunch of people in both groups that are just really not at their top game today. They're not really performing fast. They're really sleepy. This isn't going to affect one group more than the other. It's just going to make both groups worse at doing this and make it harder to see the difference, or I should say the relationship, between gender and solution time. So confounding variables, they systematically vary with the independent variable. Extraneous variables are more randomly distributed. Okay? Both really could be considered examples of noise. So let's sort of quiz ourselves here. Confounding versus extraneous variables. What sorts of things might be going on here? So let's say we had the question about which of 2 school bus routes result in a more enjoyable ride to school for the students. I'm going to go with the hypothesis that back roads are more relaxing and enjoyable. I'm saying that because I love back roads. I'm saying that because my dad taught me to love back roads by always taking the non-direct path to wherever the hell we went. Frustrated the shit out of me as a kid, but now I've come to really enjoy back roads, and I frustrate the shit out of my kids now. So how might we test this? Well, I suppose we just look at 2 bus routes, right? One that uses back roads and another that uses the main roads. And then when each kid gets to their house, the bus driver asks them a couple of questions as they get off, right? How enjoyable was that? Please fill out this survey or, give it back to me tomorrow. What possible confounds might there be there? What sorts of things might systematically vary in addition to the simple back road versus main roads? Well, obviously these are going to be different buses. What if you had different bus drivers? In the one case, you've got this sweet lady on the left, and in the other case, you've got the bus driver from the South Park cartoon who yells and screams and is upset all the time and for some reason has a bird in her hair. That could potentially affect how enjoyable that ride is. If your bus driver's screaming at you the whole time through, let's say, the main roads, whereas the person who takes you on the back roads is super sweet, how do we know it wasn't the driver that affected that and not the actual roads? Because driver, in this case, the variable of lady on the left versus lady on the right, I guess be simplistic, changes at the same time as back roads to main roads, our independent variable, this is a confound. You might also have something like bad weather that day that affects both routes, and neither group really enjoys the ride because they're both kind of scared of the slipping and sliding on the roads. This is an extraneous variable that's randomly distributed across both those groups, so you can't control for this one, you can't eliminate this one. Let's test our knowledge again here. Let's say we have a new drug. So Pfizer comes out and says, we're done with the coronavirus vaccine. We already did that. Now on our next groundbreaking research, we think we have one that cures halitosis, bad breath. You take this one little pill in the morning, and no matter what you eat, you will not have bad breath for a full 24 hours. So, how do we run this experiment? We want to know whether or not this cures halitosis. Does it or does it not? What's the independent variable? What's going to change between our groups? And probably, given that it's a drug trial, it's going to be one group getting this experimental drug and another group getting a placebo. So our independent variable, 2 levels, 2 points on the scale, variables always vary, getting the drug, getting the placebo. What are we measuring then? Well, we're trying to find out if this drug affects halitosis, so we have to some way measure halitosis. We have to measure the stinkiness of your breath. So perhaps having somebody just breathe onto the experimenter and they make a note of how bad it smelled, or breathe into some apparatus that measures some sort of particles that are given off in the breath. Our dependent variable is some measure of breath stinkiness, right? Halitosis. Our independent variable is drug versus placebo. But we could also have all kinds of confounding or extraneous variables, right? We've learned that people who have high allergic reactions to other things may have high allergic reactions to the COVID vaccine, right? That means that variable of those who do have high allergy reactions and those who don't is varying at the same time, all right? And that could potentially affect their ability to recover or react to that vaccine. We can also have all kinds of extraneous variables, and this is the point of these massive scales, or the massive scale of these studies, is to try and determine what all the other randomly popping up variables might do in an experiment. What happens if one person actually doesn't produce those particles already that produce bad breath, and thus taking the drug does nothing for them, or being in the placebo group, they still seem to show like they have no halitosis. These are the sorts of variables we need to try and account for when we think about measuring behavior. Beyond that, sometimes we can find a scale or a measurement that already exists. So let's say you wanted to measure how shy somebody was. Well, psychologists came up with a scale, a number of questions you can ask both of them and of their behaviors that you observe. They call it the shy Q. Yes, very cute. Well, one thing you have to be interested in, or I guess knowledgeable about when it comes to any measurement that you're using, is whether or not it is reliable and it is valid. Now, I'll point out that not everything has to be reliable. You want most things to be, but there are exceptions. So reliable is basically just when a test, a measurement, is consistent. So if I measure your height, and you told me you were 67 inches tall, right? 5'7", and then I use the same device that I measured your height with today, I use it again in 3 days, and I measure your height, and it tells me that you are 72 inches tall. That measurement device seems to be unreliable. It gave me different measurements at time 1 versus time 2. If instead it said 67 and 67, then I could consider this to be a reasonable indication of reliability. Some things should not change very quickly from one measurement to the next, like IQ or height, or right, things like that. I don't know, the speed at which you can press a button, right? These sorts of things should be relatively consistent over time. So, testing you once on something, testing you again using the same measurement, they should show a high degree of correspondence, very similar number, right? That's what we call test-retest reliability. And there's a number of other forms of reliability we'll talk about when we get into the sort of correlation and regression unit of the course. Now note, some things might not be highly reliable, right? Mood is a highly variable behavior, a highly variable trait. And so studying your mood on one day versus another day might change quite a bit from one day to the other, and thus you wouldn't expect as high a degree of reliability in a measurement of mood as you would in a measurement of IQ or height or body weight or something like that. The other thing you need to be concerned about is whether or not the scale that you're using actually measures the thing that you want it to measure. So let's say I wanted to measure intelligence. How do you measure intelligence? Well, there's a test out there called the intelligence quotient, okay? The intelligence quotient is reasonably reliable. So if you take a group of students and you have them take the IQ test, and then the next day they take another IQ test, right? The same form but with different questions, you'll find that their scores are highly similar from one to the next time, right? So it's reliable. But is it valid? And so it turns out that the IQ test was written by a group of individuals that at the time it was written used a lot of what they were used to as examples from, say, society or culture to contextualize some of their story problems, right? So it might be, Janie bought some apples at the farm, and then Janie brought those apples home, and her grandma made an apple pie out of them, and then 17 people showed up. Figure out how many people were fed by each apple, right? And so you get this word problem, and it tells it to you in this context. Well, the people that wrote the problems tended to be largely white, well-to-do test writers. And so the stories and examples they relied on tended to be from examples that they and populations similar to them were familiar with. And thus, groups that are outside of that cultural influence or on the fringes of that cultural boundary are less likely to be able to relate to the problems. And it turned out that they were being measured lower in their intelligence as a result of this inherent bias in the test. That means the IQ test is both a little bit valid, but a little bit invalid. It is measuring both intelligence and this cultural influence on intelligence. And that latter part is not what we want. We want just a measurement of intelligence without this other part. That lessens the validity here. Part of the reason why we measure things like GPA and IQ, and why when you applied to UM Dearborn you had to submit SAT or ACT or GPA scores, was because we think that those scores have what we would call predictive validity. We think that they accurately reflect some degree of your ability to succeed in an academic setting. And because they reflected your ability to succeed in a past academic setting, we think it will predict your ability to succeed in this current academic setting. Okay? Now, it's up to you and the data to determine to what degree your ACT and SAT or high school GPA you believe to be actually reflective of your intelligence or of your ability to succeed in a college environment. Some of that might be questionable. So let's see what you learned here. This is your brand new bathroom scale. All right, I bought this for you. I'm mailing it out to all of your houses based on the addresses on file with the registrar's office, so it should show up soon. I'd like you to take it to your doctor and have them weigh you on it. It comes in at 175 pounds. Yes, some of you are below that, some of you are above that. I don't know how the hell big any of you are. I'm just guessing a random number, okay? Every time you get on your new scale at home, though, it shows you 165 pounds. The doctor told you it was 175 pounds. You keep getting on and off the scale and on and off the scale, and you do it the next day, you do it the next day, you do it the next day. Keeps telling you it's 165 pounds. Is this scale, which is pretty awesome, is this scale reliable? And hopefully you said yes, because in this case your scale has measured your weight at 165 pounds every single day. It is consistent over time. Is it valid? That's a good question. If we assume that the doctor's scale is accurately measuring your weight, and your scale is giving you something 10 points lower than that, then we would argue that your scale is not accurately measuring your weight. It's measuring your weight along with some bias or some compensation. Sometimes the scale has that little wheel you have to correct for where the needle is relative to the zero. And so my point here is just for you to think about what it means for something to be reliable versus to be a valid measure. Okay? So that's the end of part 1. We've got one more quick little video here for the first lecture, so stay tuned for part 2. Cheers.